I'm going to start recording. My watch says it's 97 degrees outside. Goodness gracious, no wonder everyone's on Zoom. Like the Zoomers have filled the window here. Everyone here is braving the heat / extra air conditioning that's coming along with it. I told the other class, I'm going to make the same joke here, that I believe that this is Starbucks' fault. Because it's like Mother Nature said, does it look like October? No, then I'm going to sweat the pumpkin spice right out of you. Like, no, it is not time yet. It is not time for holiday decorations and pumpkin spice and sweaters. It is not. However, the rest of this week, maybe a little bit. So that's the standing joke about living in the Midwest is if you don't like the weather, wait a few minutes and it will change. So that, or wait a day at least. And I think that holds regardless of where you are from in the Midwest. At least all the places I've lived, you can characterize that way. So we have, let's see, everybody would have turned in their first homework yesterday. So I look forward to reading those. I will try to get you feedback within the next week or so, and I will send out an email when those are ready for your feedback. If you need to revise your homework, if you don't get full credit, then there is a due date for that within a few weeks or so. I forget exactly what day it is, but you're able to resubmit to get any points back that you don't have currently, other than points due for lateness. So if you're late, then you can't have those points back. But anything else, revision is a fact of life. So I heard some of the students talking a few minutes ago about how painful revising can be. It is painful. It is, especially if you're like a writer like me who chooses their words so carefully and lovingly. It takes me like a day to get a sentence out. And for anyone to say, that sentence is problematic, it's like, the hell it is, I worked really hard on it. But no, revising is part of this career. You have to be able to take feedback and change it.
I'm more so talking if people say like this whole, like, oh, I don't agree with your whole article or this whole section, you need to redo it all. But they don't say how they want you to redo it.
Yes, well that's just bad feedback, and that's not helpful. So if a reviewer two is like, I think you should have written a different paper, that's not really actionable. But my feedback will be more like, you forgot to say this, or what does this word mean in this context, or things that hopefully are easily addressable. I would like for you to leave my comments in there. You can hit like to close them or whatever, so they're like, muted, but they're still there. And to use track changes, that way I can see exactly what you fixed. And that is both for my benefit to make it easier to grade the revisions, but it's also for yours. Because sometimes I go back through and I realize I forgot to take off a point for something. And if I didn't ask you to fix it the first time, it's not fair for me to ask you to fix it during the revision. So it's for accountability from both sides. But I will take a look at those, and I will also try to give you feedback if there's any question about what you should be doing with respect to your next assignments. Because some of you I know are trying to do a lot, and I will encourage you to cut it down into something that is more manageable. Because the trick is that once you know how to set these models up for one factor, you can do it as many times as it takes so you get through all of your factors. So we'll build in a sequence here. Let's see. So we have some more identification stuff to look at, and then we get to talk about model fit and how we know this stuff is working. All right, let's see here. We went through M+ and R stuff last time. Should I go back through some of that to jog our memory a little bit? Okay, so what we are talking about right now is the process of telling your software how you want your latent factors scaled, otherwise known as part of model identification. This is slide 22 of lecture 4, which has your 4 choices. So in terms of the variance, your choices are fix the factor variance to a constant, usually 1, or fix one of the item factor loadings to 1 instead, either or. And it doesn't matter which item you pick so long as it relates to the factor at least a little bit. So we haven't looked at the fixing the item loading part yet. I believe that is new today. On the other side of the model then, with respect to the means, you can either fix the factor mean to a constant, usually 0, or fix one of the item intercepts to 0 instead. And so we will see that one as well. And what we will see in the results is that the numbers all rearrange themselves relative to what you have decided 0 and 1 mean. So I use the analogy of setting a key when you're trying to play or sing a song. Nikki, you had said plant your flag, I think. I like that one too. It's just the idea of like, what does this number mean? And everything else will rearrange itself relative to that number. So the first way that we looked at setting up the models then is what I call z-score factor, or standardized latent variables is the term that they use in R, where this is page 2 of example 4 that we've been looking through. I'm setting the factor variance to 1 and the factor mean to 0. That means that I can estimate all of the item parameters. So before we get into the code, what does each item get its own of? 3 things. What are they? Intercept. Yep. What's one? Not mean. That's what's going in terms of data. What's being estimated per item? Intercept is 1. What's number 2? Loading. Yep. And number 3? Error variance. Yeah, the variance of the errors. Yep. So for every item we add to the model, there's 3 things we're going to estimate. In a single factor model, it works out that way. In a model with more than one factor, we also would have to count out the factor covariances. So this way, we're identifying the factor with the mean 0, variance 1, all loadings and intercepts are estimated. Error variance is all estimated regardless. So that's not tied to identification, they just show up. So this is M+ code that I'm looking at. So to define a latent factor, you got to give it a name. Name's up to you. Choose a name that means something, so long as it's 8 characters or fewer. By is the keyword that means, hey, this thing's latent. What is it being measured by? And then you tell it. So I've got 6 items measuring forgiveness of situations here. The R at the end of items 1, 3, and 5 is to remind us that they were reverse coded. So this analysis is happening on the data in which higher means more forgiving for all the answers. That is a preliminary step you would always want to do. And I have a star in M+ behind each of these because that means estimate loading. You don't have to type that for all of them except this, the first one. But I have it here for all of these to be transparent. The intercepts are the listing the item in brackets. Error variances are just listing the item by itself. And then at 1 for situation means fixing the factor variance to 1. At 0 in the brackets means fixing the mean to 1. And if you want to type less, all you would really need are just these 2 lines right here. So the green, by the way, these are comments meant to describe what the code below is doing. You don't have to type them, but if you are somebody who wants to leave a trail of breadcrumbs for yourself, when you come back to this a year from now, I would highly recommend putting in the comments and changing them to be appropriate for whatever you're trying to do rather than just copying my comments. This can also make your code easier to read for other people. If you want to share code, particularly like in an appendix for a paper or something, if you want to give the code, having your code clearly labeled will help out a lot of folks. So all you really have to type in M+ is this. The star right here, you cannot forget that one though, because by default, M+ fixes the first factor loading to 1. The star overrides that default. And then I have to fix the factor variance to 1 because by default it's estimated instead. So then we looked at output. All of the loadings are significant. That is almost always going to be the case. We don't really care about p-values much in this context. It looks like the ones that are reverse coded are a little bit higher, but these are on the scale of the original variables, and so we can't look at these numbers and compare them directly. We have the means for the factor, we have the intercepts, and because the factor mean is 0, these are the item means, which may have been what you were thinking of in terms of estimated parameters. I'm going to keep saying intercept though, because the difference is that intercepts are conditional. They will become the same values as the item means if the factor mean is 0, but only in that case. So they are still, these are conditional means. Variance of the factor, and what does it mean if you see this 999? Remember that one? Is that a number? It is not. It means this parameter was fixed, so I don't have a test statistic because I didn't have to estimate it with any degree of error. And then residual variance. What are these things conceptually? Item residual variances. Go for it.
That's the part not associated with the factor.
How much of the item's total variance is not associated with the factor? You can call it error, call it residual, call it specific, call it unique. I just say not the factor. I don't know what it is, but it's not the factor. So then we looked at how this model tries to recreate the variances and covariances and means of our items. And the formula for recreating an item's variance, let me make this a little bit bigger. It's the unstandardized loading squared times the variance of the factor plus the variance of the error for item 1. So the loading for item 1 was estimated at 1.234, so I square that, multiply it by the variance of the factor, which we fixed to 1, and then the estimated error variance for item 1 is 1.526, and the total variance is 3.049. So in the chat window, thank you, Ahmed, we did the math here of what 1.234 squared is, and it's 1.523. So roughly half and half of this item is due to factor versus not the factor. In terms of how the factor model predicts covariance, it's the loading for each of the items times the variance of the factor that they have in common. So this will differ once we move to two-factor models, but for now it's just this much. Loading times factor variance times loading. That gives us the predicted covariance between these two items. And I have a note that in the data, the actual covariance was only that much, so the model thinks these two items are more related than they actually are. That's our first indication that this model isn't going to fit that well. Okay, so this is the unstandardized solution. The job of the unstandardized solution is to recreate the item means, item variances, item covariances. If we standardize all of these coefficients by saying, what if all of the items had a total variance of 1 and a mean of 0, and what if all the factors had a mean of 0 and a variance of 1, then we get to what is a separate piece of output in M+, the standardized results right here. So standardized factor loadings, that's what we get here first. These are correlations. You can interpret these as a Pearson correlation between the item response and the factor that it's supposed to measure. Because each item is only being predicted by one factor, so the relationship is its full bivariate relationship. So the standardized loadings tell the same story of relative importance, and here we can look across these numbers and make informal comparisons because they're all on the same scale. The reverse-coded items are actually loading more highly than the not reverse-coded items in this factor solution. Nobody cares about standardized intercepts. Residual variance, this is out of a total variance of 1, how much is not the factor? So these are proportions of unexplained variance. So 50% of the first item is unexplained by the factor. 74% of the second item is unexplained by the factor. And if you want to get to the part that is explained, that's R square. And yeah, these are telling you the exact same thing. So for item 2, for instance, 74% is unexplained, leaving 26% explained. So these are your effect sizes. It's not enough to know that the model fits. We also want to know the extent to which each item appears to contribute in the way that we thought it would. So in CFA world, more is better. So items with a stronger R square or a stronger standardized loading are considered better items, more discriminating. And what is the relationship between standardized loadings and R square? Do you remember?
That's the same.
They're related. They're not exactly the same. They tell you the same thing, though. How do I get from one to the other? If a loading is an R, then how do I get to R squared? Square it. Yes. Yes. It's 217, and I'm throwing softballs left and right here. Square it. Yeah, boom.
I'm worried that it's only Tuesday.
I know
This
it.
is where I'm at.
It is Tuesday. Happy Garbage Day. That's right.
Speaking of garbage day,
Mm-hmm.
when are we gonna
See the merch? Yeah. Well, he made me a long sleeve t-shirt, and as long as it's 97 freaking degrees outside, you will not be seeing long sleeves on me. Yeah, well, so honestly, like standing here, I get really warm. And I don't know if it's just like the computers or the lack of circulation or the fact that for me, teaching is an aerobic exercise. No, seriously, like I burn about 300 extra calories on the days that I teach. And that's not just walking, it's like it happens at home too. So I'm warm. So maybe November will be sleeves by then, maybe. But yeah, I can't wait to walk around the hallways and see people's expressions like, what? Why does her shirt say Happy Garbage Day? But I don't know. We'll find out. But yes, throwing softballs, standardized loadings are R's. You square them, those are your R squares. So that means in practice, you really only need to report one or the other. Which one? Take your pick. Okay, so I think that was where we left off. We looked at Lavon code. So yeah, well, that's not quite where we had left off. And the thing about Lavon code is that you have to type what would be the entire M+ model input essentially into one quoted string and take that string and send it to the Lavon function. So the differences, the word by in M+, let me zoom in here to get the marks, is equal squiggle. Squiggle meaning the tilde that is the shift key on the top left of your keyboard there. That's where I find that one. And then we list the items that contribute with plus signs in between, which drives me nuts because plus signs is not what we're doing here, but that's okay. To refer to an intercept, it's just the squiggle by itself, the tilde and a 1. To refer to a variance of any kind, it's the two squiggles next to each other. And to refer to a covariance, it will be like one word, squiggle, squiggle, a different word is what covariances will look like. We'll see those in a minute. And this part right here is fixing the situation factor variance to 1. So 1 star in the front, that is a fixed parameter. It is backwards to M+. Come on, Lavon, come on, man. You couldn't have an at symbol? Is at mean something else in our language? Is that one already taken? Anyone know? Zoomers? So they could have, and they're just being mean to you? Is that what's happening here? Well, job security is also what's happening here. You learn this, someone's going to pay you to not have to learn it. And then this one, I'm fixing the factor mean to 0. So this line is standardizing my latent variable. The option right here at the end of the call, standardize.lv equals true, does the same thing. So my code is somewhat redundant, but again, I'm trying to be transparent. So I ask it to estimate a model using Lavon, and then I print the summary of it where I'm adding additional pieces of information, including the standardized solution and the R squares, and fit, of course. And just like M+ has a shorter version of the code, this single line is all you would really need to write. So when it comes time for you to actually estimate these models on your own using either my data or your data, I don't care. You type as much as you want. You just have to realize what defaults are being invoked when you don't mention them specifically. So I'm using the SEM function instead, which invokes a series of defaults that Lavon does not. And from what I read, the CFA function does the same thing. SEM and CFA basically do the same. There are others that talk about growth models or other specific cases that we're not doing here just yet. So then the R output looks remarkably similar. The only exception is that the standardized results are at the end of the column here. So you don't have to have two different sets of tables, but otherwise the numbers do all match to 3 decimal places. Hooray. And then the other thing that I noticed is that if it has a dot in front of it, it's conditional, it's an intercept, and if it doesn't, it's a mean. And the same thing down here, the dots refer to residual variances, which are conditional variances, as opposed to situation, which is just a regular variance because it's a predictor. And that, I think, is where we left off. Okay. Questions or any of that you want to hear again? As a reminder, all of the original input and output in both programs is in the download folder that goes with this handout. So this is just the summarized, annotated version. You can follow along with those or play along with the models if you wish. Okay. So we just did, let me find my slides, the top left box. Okay? That's what we just did. Now I want to show you what it would look like to move to the top right box, which is change the identification such that the factor variance is estimated and one of the loadings is fixed to 1. And we'll see how the scaling of the model changes as a consequence of that. I have a question. If the scale contains many items, 20 plus, do we have to type them all? Depends on your package. So in terms of saving more typing, let me go back to the M+ code. Here it is, for instance. So if I didn't have the R's at the end, I could type even less. I could say sit by sit 1 dash sit 6, like that. I don't have to write them all. And it would understand that I mean all the ones in between. So in M+, I know you can do that if you name your variables in that way. In R, I think you should be able to, but I don't know how. So if there's any other abbreviation system in terms of like sets of variables that R already takes, it's probably in there, but I don't know how. So sorry, got to do more typing. But this does work because I do rely on that quite a bit. If you find out, let me know, okay?
Okay, thank you.
Yeah, I want to know the answer to that too. Because I've got some examples with a lot of items coming up and I don't want to type them all. The other thing that you can do to make your life easier is, like, I have sit as the prefix. You could just call this I or S, right? You don't have to have words. You can have the names be as short as you want where you know what they mean. Okay, so now here we go, Model 2. That's where the new stuff is. So page 6, starting with that. So we're changing the scale of the model to the default traditional version, where the first item's loading is fixed to 1, the factor variance is estimated instead. So the changes to the code are in M+, this line and this line. So I've got the notes as to what these things mean off to the side now, so we can look at it a little more easily. At 1 means make it 1, fix it at that number, estimate all the other loadings. Still estimating all the intercepts, still estimating all the residual variances, because I've fixed the factor mean to 0 still. So intercepts and factor mean go together, loadings and factor variance go together. So sit has a variance that's being estimated because I fixed the first item's loading to 1. And the analogous code in R is that part right there and that part right there. So 1 star situation 1R means fix the first factor loading to 1. And then I'm estimating the variance instead. So I've called this Model 2. Is this going to give me any different information? No, it's just on a new scale. So previously, the latent variable was scaled such that 0 is the mean and a standard deviation is 1. Now I'm going to have an estimated standard deviation because the variance of the factor is going to become the amount of variance that is due to the factor in the first item. So here are the results. First in M+, I think, do I have R output? No. Yeah, the R output is so much the same that I didn't put it in. But there's your clue that you have asked for the first item's loading to be fixed at 1. And I know that that's okay because I also see this at the bottom of my page here. So in your homeworks, when you have your own data, I'm not asking to see the data. I'm asking for tables that look like this. And I will know right away if you screwed this up if I see ones in both of those places. Okay? If I see ones in both of those places, then that's a double constraint. You've said not only is my factor standardized such that the standard deviation is 1, the first item is perfect. Not cool. Unless it is, but that's a test, right? Perfect is not usually what we go for. So, okay, now the number, 1.523. That's the number. Thank you, Ahmed, for putting it in the chat window. Now, where did that number come from? 1.523. That number, that comes from the marker item. That number is the loading of the first item squared. The amount of the first item's variance that was due to the factor is 1.523. The error variance for that item was 1.526, giving us back to the total. So this is the part of that item's variance that was due to the factor. That becomes the factor variance. Note to self, next time put a text box for this, so I don't have to scroll through 12 pages. So now, what is a standard deviation of a factor? Like, what does a 1 unit change in the factor mean? How much is that? Well, yeah, so essentially, we have to know what the square root of 1.523 is. Anyone got their calculators? Want to do the next one? Square root of 1.523? Did I say square root? Yeah, I did. I'm bringing the Midwest back strong today. That us native Midwesterners are allowed to say square root. Sounds totally fine to me. Everyone else is horrified.
It's 1.234.
1.234. Because we just literally covered that. Thank you. Checking my math, though. 1.234 then is my standard deviation. So now a change in, a 1 unit change in the factor is 1.234, like for a standard deviation. So 1 unit is less than a standard deviation. But in terms of the conclusions that we would come to, previously we said that the items that were reverse coded loaded relatively higher, they still do. What the numbers are has changed because what 1 means has changed, but they're all relative to that as a new reference point. See, I told you I was throwing softballs, 1.234. That's a real number and everything. I didn't even make that up. Yeah. So the unstandardized loadings have changed because they convey what the change in the item response is for a unit of the factor, but what a unit is a different number. And now you can probably guess why I don't tend to do it this way, because I don't want to have to keep track of what a unit is. A unit being 1 is much more convenient. Otherwise, though, the mean of the situation factor is still the 0 I told it to be, which means the intercepts are still the item means, and the amount of variance that's not the factor in each item is exactly the same. And I did not have the standardized solution because it would literally be what was just on the other page. It does not change 1 iota. Oh, I do have the R output. I have a little bit of R. Because I wanted to point out this much. Rather than having the 999s, it just blanks this out. So if you don't have a standard error, that is a fixed parameter. And then last but not least, here is another choice. Now we are moving to the bottom right. So this is where we are borrowing the scale of the first item with respect to not just the loading, but also its intercept. So the factor mean gets estimated and the factor variance gets estimated. So in M+, the difference relative to the previous model is right here. The first item in brackets at 0, that's its intercept being set to 0. And the factor mean being estimated is situation in brackets. In Levon, it's right here and right here. So I find this a little bit confusing. To shut off an intercept, it goes to 0. To turn it on, it goes to 1. But it's not fixed at 1. It's just estimated. And then here's what we get back. The mean of the factor is now the mean of the first item instead. And the intercepts are all kind of crazy. That's because they are expected values when the factor is 0, but the factor has a mean of 4.5. So 0 for a factor score is outside the scale of the data, which is why these are weird. And in R, we see the same thing, blank spaces for the fixed parameter at 0. So, point of the story, how you identify the model does not change the conclusions you would draw about how good it is and how good the items are. It just changes the scale of what the latent variable means. I've got the hybrid today. We have the Diet Sunkist, which has half as much caffeine as the Diet Mountain Dew, but more than the Diet 7-Up that I thought I probably should have had. So we're splitting the difference here. Highly recommend. Orange soda. It's not just for children. All right, questions? Zoomers, how we doing? I see a couple of you hanging in there. I promise I won't make you get your calculator out anymore. At least not for the next 5 minutes. Is this making sense? Relatively? Okay. So what we've seen so far is what the model looks like if we assume a single factor is responsible for the pattern of covariance. We have not seen how accurate that is, though. We haven't talked about that yet. So we've looked at effect size with respect to how good the items load. We haven't looked at basically model fit, is where we're headed next for this. So that is the next thing that we have to talk about. All right. So let's see, as I'm looking for stuff, we have to talk about estimation a little bit first. I'm sorry. The softball portion of the program is over. Now we're going to start throwing hardballs a little bit. But just before we dive into that, how many items do you need for a single factor model to be both estimable and testable? 4. How many, to just have it be estimate and not break? 3. And what happens if you have 2? Set the factor, yeah, set them equal to each other, and then it's not under-identified. So, yep, keep that in the back of your mind here. All right. So I'm starting then on slide 32, and I'm going to be honest, I'm not going to spend a whole lot of time on estimation because that's not my jam. For these sorts of models, it tends to be super quick. So it'll take just like a split second for these things to run because of the magic of CFA. Those of you who are in the Bayesian psychometric class will get to learn a whole lot more about estimation because Bayesian takes maximum likelihood and adds priors to it. So it's what I'm talking about is essentially nested in terms of that level of complexity. But I do have to talk about a little bit of where the numbers come from and how that ties into model assumptions. So I made this joke last time, the idea of a black box. So what happens behind the scenes is what we're talking about. And when you run M+, literally a black DOS window pops up as the model is churning and then it comes out. So in terms of estimation, we have to figure out first what all is being estimated and what's fixed and what's random. So in the example that I have in this PowerPoint, which is actually what we're going to have in the example too, is 2 factors. Each factor has 3 items, and when I put them together into one model, it is over-identified because I have more covariances than I'm estimating factor loadings. So I'm still over-identified in this case. So if I have this model that I had in the diagrams that go with this lecture, I've got 6 intercepts because I've got 6 items. I've got 6 factor loadings because each item only measures 1 factor, By the way, there's a word for that. It's simple structure is what that's called when each item only measures one thing. And it's desirable in a lot of contexts. I also have 6 error variances. And if I've estimated all the intercepts and all the factor loadings, that means that I must have fixed the means to 0 and the variances to 1 in order to estimate everything for the items. But I do pick up a factor covariance. So in total, there would be 19 things that have to get found in the output. So in these models, in psychometric models in this class and most of the time, item parameters are considered fixed effects. That means that we take an item and we only make an inference about it. Like the loading for item 1 is 1.234, the end. I'm not trying to say what would it look like for any other item, it's just this is my inference is about this one. So we're treating items as fixed. We're treating people as random. So even though each person has a factor score, in theory, that is causing them to answer these questions in the way that they have, person-specific factor scores are not things to be estimated. All we need to know is their distribution. As long as we can make an assumption that the factor scores are multivariately normally distributed, then that mean, variance, and covariance across the factors is sufficient statistics to do everything else. So if you want to know what the factor score is for each person, you have to ask for it to be predicted after the fact. It's not estimated as part of the model. And that is actually true of IRT as well, but they don't tell you that. It's not a model parameter. So no matter how many people this analysis is based on, it's 19 parameters based on the number of items, because items are fixed. So the process then, in terms of what's happening under the hood, we try to figure out what values of these parameters work best, are most likely. We try to figure out how likely they actually are relative to other possibilities. And then based on what we've found, we have summary information as to how good the model is that we use to compare across alternative models. So those are the 3 basic steps. But where all of this starts from, in this section of the class, CFA, is our friend the univariate distribution, univariate normal. So I stole this from Wikipedia a very long time ago. It's still up there. It still works. So of all of the distributions, this one has, I think, the hardest formula, which is sort of funny because it's the one that gets started first. But there are 2 parameters to a normal distribution, right? Mean and variance. Given those 2 things, I can compute a value from this function that describes essentially the probability of observing any particular outcome value. So the word here is likelihood because it's a continuous distribution, but you can think of it in terms of probability, which goes with discrete, where I'm literally talking about the height of this y-axis right here. So if the data follow this blue line and I have a score of 2, that's not very likely. If the data follow the red line, it's more likely, and if the data follow the orange line, it's even more likely. So given mean and variance, I use this formula to compute a number for each person that summarizes how high they are in their likelihood. Under the assumption that people are independent, I can then multiply those likelihoods together, the same as we would with independent probabilities, like coin tosses and stuff, right? What's the probability of 2 coin tosses that you get, 2 heads, that kind of thing? You multiply them together. Same thing here. But the problem is that these numbers get real small real quick. So to preserve numeric precision and to make the math easier, we take the log of the likelihood and then we can add them across people. So this idea of log likelihood, height, bigger is better. It means that the data are more likely, and not just your data, but everybody's put together into one pile. And this is what it looks like for one outcome at a time. So within this normal distribution formula, we have y hat here, the conditional mean, given the predictors, and sigma squared, which is the residual variance. What we need to do, though, is transform this into multivariate space. So here's an example that I built for a previous class, just showing heights, and you can download this file from that class. This is the generalized linear model class, where in Excel, there is a function called normdist. And given a mean and a variance, you can compute the height of each possible answer here, take the log of it, add it across people, and you end up with a value that's log likelihood. So most of the time, log likelihood is going to be negative because it's in log space. It's tiny, tiny numbers. But you can compare that to any other possible value for the model parameters. So for instance, what if I said the variance is actually 5.2 instead of what it's supposed to be and the mean is 2? Well, that set of heights is shorter overall. Taller is better. And I have the function here across the values of the outcome. For some people, the red line is taller, but not for everybody. So this idea of trying out different values of the parameters and then seeing how tall it makes the data, and then try out a new set and see if it makes it taller, it keeps going through this over and over again until it figures out like what values are optimal to make it tall. And you don't have to do it through brute force. There's ways to use calculus to figure out which side you're on, whether you should be going up or down. I don't want to get into the details on that too much, but the idea is height. So this value that you're going to see on your output log likelihood, it's the combined height of the data given the model parameters, where it tried out other versions, and this is the best that it could do for that model. Most likely, height. Where we're at, though, is more than one answer per person. So the formula for height has to adapt to take into account joint height of however many item responses a person is contributing to the problem. So the multivariate normal function for height looks similar, but it has a few switches to it. Number one is, instead of just residual variance, we've got sigma here, which is the predicted variance covariance matrix from our model. That shows up here, and it shows up in the middle of this part here. And rather than having a single y-hat, we have a bunch of them, one for each item. But it's still the same basic idea. We need to know the means, variances, and covariances of the data as they are predicted by the model. So how do we make sigma? This is the answer right here in this little box, but it's built from the loadings, and it's built from the error variances. So loadings times factor variances and covariances times loadings transposed so that the math works out, then you can add it to the error variances and you get sigma. So sigma is being built, is my point. Sigma is the total recreated, predicted, what the model says it should look like version of the data. So we would try out different versions of all the model parameters that would make different sigmas, see how tall it gets, and then land on whichever versions make the joint distribution of everybody's data the tallest. That's my quick and dirty version of this. But what I want you to hang on to is the idea of height. Height is the thing. So we can rearrange that PDF for the multivariate normal into something that looks more like this. And here is how we compute height for these types of models, these SEMs. When the program decides that it's as tall as it's going to get, it outputs the answers. And those are the estimates that you get. Next to the answers are indices of imprecision. And those are actually going to be based on the shape of this height likelihood. The idea of trying out different possibilities and seeing which one is the tallest. The shape helps us indicate how precise it is. So the standard errors actually come from this process as a byproduct. And I have the keywords that you will see when you read technical definitions about this. It is built from a matrix of second derivatives, which in terms of height is the shape, is how quickly the slope changes as you get to the top. And those of you who are from the hard sciences are like, oh, come on, Lacey, you're butchering this, but I'm trying. Height. Height's the key idea. That's what I want you to hang on to. So flatness is essentially indicated by standard error. So then we have, well, okay, I've got the parameters that make the data how tall they can possibly be. Well, what do I compare them to? Well, the right answer. How tall would our data be if we literally just recreated the covariance matrix? If we didn't try to predict it, if we just let everything be what it wanted? Rather than trying to estimate loadings that predict covariances, what if we just let the covariances be whatever they want? And rather than trying to have intercepts that predict means, let's just let the means be what they want. And rather than estimating error variances to try to fill in how much is not the factor, let's just let the variances be whatever they want. That model, the be whatever it wants model, has a special name. It's called the saturated model. And for those of you in the other class in longitudinal, saturated refers to both the means and the variances and covariances in this context. Everything gets to be what it wants. So unstructured variances and covariances plus saturated means is the saturated model in SEM. And that's as good as it gets. So we have the height of just the data, which is S, relative to the height of the sigma, which is predicted by the model, and we literally take the difference. So you will see this formula in your textbook and in other technical sources describing the fitting function as it's known. This is for complete data only, by the way. But where the chi-square test statistic we're going to look at in terms of the difference in height comes from, this is a shorthand version, but it's essentially a likelihood ratio test relative to the perfect model. So we have S. S is for saturated. That's what the highest possible height could be for our data. We have sigma that our model says, which is the best height we could come up with given the way that we set up the model. How close are they? That's our index of model fit. How close did we match the original data? So we use these heights to compare against alternative models where one of the alternatives is the best possible thing you could ever have, which is saturated, and others are plausible alternatives that you might want to test. Like, am I measuring one thing or three things? Like Kaylin's going to test that, right? Is there only one way to screw up your kid, or are there three distinct ways to screw up your kid? Right? Three, yeah. Actually, there's more. There's a lot more than that, trust me.
Infinite ways to screw up your kid.
Infinite, yes. Many, many ways to screw up your child. Another question you might ask, are all of my items equally good so that I can just add them up and call it fine? That's a comparison, because then you'd have one loading instead of 6. You'd see how tall your data get from one loading, compare it to how tall they are for 6. So this model summary of log likelihood is the thing that helps us to do all of these empirical analyses as to how our choice compares to the best or among other possible alternatives. 1 factor, 2 factor, which loadings, et cetera, et cetera. So this idea that these models assume normality of the item responses. Remember, CFA is like linear regression, where Y, the item responses, are supposed to be normally distributed and continuous variables. The reason for that is because the formula that we're using for height is the multivariate normal formula. So it's somewhat tautological, like, well, we have to say that the data are normal because that's how we're judging height. If the data aren't normal, we need a different formula for height. So for instance, if I had binary answers, should this work? Probably not. In binary data, and this is coming in a couple weeks, the mean and the variance are not separate parameters. In binary data, the mean tells you what the variance has to be. It's the mean times 1 minus the mean for a single binary item. So rather than having a multivariate normal likelihood, we're going to switch it out to be Bernoulli, which is appropriate for binary answers. And then that's the new way that we indicate height. Or if I have ordinal data, then I need multinomial as my formula for height. If I have count data, I need some kind of count distribution as my formula for height. So the assumptions are baked into the way we index height, is where I'm going with this. So if it doesn't fit, you change your height formula. And this also allows you the flexibility to have continuous outcomes mixed with binary outcomes, mixed with count outcomes, mixed with all the things. Each one can have a different formula for height. All right. So persons and items are conditionally independent. That's one of the things we assume. Items responses can be missing at random is another assumption. What that means, by the way, missing at random, is conditionally random. Meaning, after I know what they answered for the other choices, then it's random, conditioning on that. Like among people who answered this way. So it's not completely missing at random, which is what other estimators assume. We're also saying factor scores have a multivariate normal distribution. That is always the case. In this model, E's have a normal distribution. We're going to switch that out when we get to different kinds of items. And so the whole thing is multivariate normal because a normal F plus a normal E is multivariate normal. So what are the consequences then of having item responses that are not normal? One is that the linear model just doesn't work. It will predict item responses that go past the scale of the possible outcome. And another consequence is that all of the standard errors and all of the likelihood ratio tests fit statistic comparisons that are based on this idea of height from a normal distribution are going to be off. So there's 3 different ways that we can fix it. The number one way that we're going to use in this unit is robust maximum likelihood. That's MLR. What it does is try to adjust all of the fit statistics and all of the standard errors for how far off from normal you are. It's actually kurtosis that's the problem, not skewness. Craig Ender's book, Chapter 5, is on your reading list, explains how this works in much greater detail than I'm capable of. So for item responses where it's like, it's normal-ish, like I'm willing to believe that, it's like symmetric, but it's still kind of ordinal, robust maximum likelihood is what people would typically recommend. For something like binary, absolutely not. Absolutely not. We need a different kind of factor model for that. We got to switch out how we talk about height, and at the same time, switch out how the factor can predict an item response that can't go past 0 or 1. The boundaries shows up again via link functions. So MLR then, otherwise known as these people's invention from a bunch of years ago, it's still a linear model. So you're not changing the way that the factor predicts the item response, you're changing the way that the standard errors are computed, essentially. And the good news is that you get this thing called a scaling factor as part of your output, where 1 means perfectly multivariate normal. So if you're in the situation where regular flavor multiple maximum likelihood is fine, this doesn't hurt anything. It simplifies to that because the scale factor just adapts to that. Most of the time what you'll see is a scale factor that's greater than 1, which means a flatter distribution relative to something that's too thin. So MLR is what we're going to use by default in all of our estimation for CFAs. This also, though, entails an extra step to the likelihood ratio test that we're not used to seeing, at least relative to the ones that you would have seen prior to this class. I have a note. Let's see. Stata folks, this is for you. I know, woot woot. I didn't forget about you. So this is current as to status 16. I want to say they're up to 17 or 18 maybe. I have not looked to see if this has changed. But this is my taking apart all of the documentation that I could find with respect to what it allows. It does have regular flavor maximum likelihood with no missing data. It has this thing, which is full information maximum likelihood, but you don't have a choice as to what's in the likelihood. Everything is. They have this thing that no one ever uses because it takes thousands of people. And then they have options for robust standard errors. So there doesn't seem to be a combination that allows the scaling factors and the robust standard errors and missing data like all at the same time. So that's why I'm not showing Stata. Also because, damn it, I'm already doing 2 programs and 3 is a lot. But if you want to use Stata for your own data, that's fine. Just know that you may not get the exact same results because of the differences in how it's estimated. So I'm fine with that. I've grown to like Stata quite a bit, actually, and after teaching with it. Question, how do we test normality of item responses at first? You don't. There are tests for it. From what I understand, they don't work well. They're highly sensitive to sample size and other types of issues. The way that I approach it is to look at how the factor model predicts item responses, and do they go out of bounds at plausible values of the factor? If so, then you probably need a different model. There is a whole lot of literature, though, on this, looking at what point is something normal enough to get by with CFA. Like, there's a whole lot of literature on that. So it varies by what they've manipulated in those studies, but to me, it's like it boils down to, is a linear model a plausible thing? If not, pick something else. All right, so 258, that wasn't too bad in terms of time spent, not in terms of anything else. Switching back then, so big picture, height. We have the parameters that make the data the tallest. Now we got to see just how tall that is. Relative to what? Model fit. Relative to saturated, exactly. But there's going to be relative to other stuff too. Because just like there's a best possible, there's a worst possible. And so some of the fit indices are going to say, how much worse are you than perfect? And others are going to be like, how much better are you than terrible? And they're not going to agree, right? Because those are two different questions. So, in terms of where misfit comes from, recapping parameters and data going in and out. To the extent that each item gets its own intercept, the means will be fine. To the extent that each item gets its own error variance, the total variances will be fine. So sigma predicted and S saturated are going to match exactly when it comes to means and variances, so long as you let each item have its own. In this class, I've seen instances in which it doesn't, but not in the context of factor models. Covariance is where the problem comes in. That's where your degrees of freedom show up. You are trying to recreate more covariances with fewer loadings, and that's where you can be wrong. So here are the choices for worst and best in this class. In the context of measurement models for the purposes of latent factors, the worst model that you would consider is what's known as an independence or null model. And this one lets all of the variances be what they want. It lets all of the means be what they want, but it says no covariance whatsoever. So this isn't really a model. This is a statement that says your data have nothing in common. Prove me wrong. Like that guy on The Daily Show, I can't remember his name, but there's a comedian on there who sets up like a table in New York City, and the table says something egregious like, chocolate's terrible, prove me wrong. And then he gets into fights with people. But yeah, this guy would be like, your data have no covariances, prove me wrong. And then over here, on the other side, is the saturated model, which is, no, let everybody be what it wants, it's fine. So this is all the parameters being spent. And our model, somewhere in between. Our objective is to recreate the saturated model using fewer than all possible parameters. And that, in turn, allows us to make a theoretical statement about whether our items measure one thing, or two things, or three things, whether they do it equally well or differently, etc., etc. And for those of you who've been with me all afternoon, yes, this is the same slide I showed you earlier in that context. It is the same. Saturated is unstructured 2 hours ago. So here are two pieces of output in terms of fit that we'll look at. I have M+ first and Lavon second because, of course, they put them in different orders. So first, M+. So the first level of summary information is going to be comparisons of those two baseline models. So number of free parameters it tells you first, that's the number of things being estimated. So the 18 would be, for the example with the forgiveness items, 6 intercepts, 6 error variances, 6 loadings, that's 18 for one factor. So log likelihood then is height. And I've got two flavors of it here, HO and H1. Now look at these numbers, negative 11,536. Is that good? Who knows and who cares? It doesn't mean anything in absolute value. it's a largely negative number. Let's put it that way. It's a very small number, actually. Very far into the negative side because of the logs. So this is the log of the multivariate height across all 1,000 people in my data set. So I've got HO and I've got H1. Now, for many years, I actually struggled to remember which was which. And then something happened that made me never forget again. Can I tell you the story? It's a good story, I promise. Some of you have heard it. So I had a student, this was at Nebraska, her name was Lindsay, and I was running office hours in a computer lab like this one, so there's like 20 people in the room. Some are working on one class, some are working on another class, and I'm going around the room helping people troubleshoot their code and stuff, and I'm working with the student, and she looks up and she says, "Am I the hoe?" I'm like, "What?" In M+, am I the hoe? "Oh, you mean, is your model the HO value as opposed to the H1 value?" "Yeah." "Yes, Lindsay, you're the hoe." Carry on. So just remember that. You are the hoe. That's it. That's my story. H1 is the perfect model. I don't know where the names came from. It's sort of like null and alternative hypothesis, but when I try to put the words on that, I have a hard time. So just, you're the hoe. Let's go with that. So these numbers are different because the saturated model has all possible parameters to it. So that would be 6 variances and however many covariances there are in here. Way more than the 18. Actually, I don't even have to compute it. 18 plus right here, it tells me I have 9 left over. So there's 27 in total. So I could have spent 9 more, but I didn't. So I have the log likelihood for my model is the hoe. The saturated perfect model is the H1. And this chi-square right here is the log likelihood comparison. It is a likelihood ratio test. For those of you who are good at math in your head, you might look at this and say, this isn't the difference between these two numbers. And it's not the difference multiplied by -2 either. The formula for likelihood ratio tests in MLR has to use these scaling factors in it. So the formula can't be done in your heads very easily, unless you're a savant. But good news, if you're using M+, I built you a spreadsheet. If you're using R, the ANOVA function does it correctly. So you don't have to type any numbers in. But that's what this is telling you. 308 is how far away from perfect our one-factor model is. Where 308 is evaluated based on how many parameters we didn't spend using a chi-square distribution. So its p-value is 0 to 4 decimal places, meaning wildly significant. So is this good news or bad news? Bad news. Significance is bad in this class, okay? It's a switch in thinking, because what it means is you are significantly worse than perfect. Yeah, that's what it means. And yeah, and we sort of giggle because that sounds ridiculous. But the fact that perfect is our standard, what's coming next on Thursday is, well, maybe perfect shouldn't be our standard. Like, maybe good enough should be our standard. Can we compare against good enough? Yes, we can. That's a different fit statistic. But yes, we are significantly worse than perfect. So this is a chi-square value that is a test statistic. So you can think of this as the difference in -2 log likelihood that's been rescaled by these scaling correction factors, or you can report it as a chi-square, your choice. And you would report the scaling factor that goes with this test as well. The other one that's on this page is right next to it and labeled similarly, but it's confusing potentially. This one you will probably never care about in your life. The chi-square test of model fit for baseline is the difference between the perfect model and the worst model. It has nothing to do with yours. So what that test is telling you is whether there is any covariance in your data worth modeling. Significant means yes.
So you're significantly better than the worst.
The best is significantly better than the worst. That's what it's telling you. And none of it has to do with you, because it's not your model it's talking about. So I don't even know why it tells you this. Nope, because neither of the models involved in the comparison are yours. It's literally a comparison involving your data. And the only way that I can make any kind of sense out of this is it's telling you if you have something worth modeling. Because if the best model was not better than the worst model, that would mean your covariances are basically 0. And if your items are not related, game over for making a latent factor out of them. So that's the only way that I can rationalize why this shows up. I know. R folks, this one's for you. And this is where I wish the folks who made Lavon could maybe add a few more words to the output. This maybe. So they put the regular flavor ML output in the first column and the robust output in the second column. In this class, use the second column. But this will give you a sense as to how the conclusions would change if you didn't correct for any multivariate non-normality. So the first thing that it tells you is minimum function test statistic. You're just supposed to know that that is your model against the saturated model. So that's the 307 that was on the previous page. And yeah, 307.804 versus 307.799 is going to make my life hell for the homework system. I know this, and I'm going to fix it. I'm going to make sure that it works. But the regular chi-square is 427. So the model fit actually looks worse if you don't correct for the non-normality in this case. Then we get the degrees of freedom. That part's self-explanatory. P-values saying significantly worse than perfect. Then we get model test baseline model, which is the same useless version from the previous slide. So you can ignore that page. Then we get a bunch of other stuff that we haven't talked about yet. And then we get into the HO versus the H1. And these numbers work. So these ones are spot on with what M plus does. So I can use these ones at least. Hooray. I don't actually try to make your lives hell. I really don't. It's just that in trying to like make my package do all the things, right? It can't do all the things to 3 decimal places. Then we get into AIC, BIC, and another BIC. These are opposite in direction. Smaller is better. Because they are based on log likelihood times -2, and then corrections for number of parameters, and it's the same stuff from before the previous class. So smaller is better with respect to these. They're used for comparing non-nested models. Bigger is better with respect to log likelihood. All right. So that's the part that it gives us. And we can talk about the rest of it, I think, next time. Judging by the number of times I'm seeing people look at the clock, I think we're out of energy for today. All right, and I'm out of softballs to throw you. So, any questions before we call it a day? Zoomers? I'm trying to catch up with the chat. I think I'm caught up. Good. All right, then I say I will see you Thursday. Let me know if you need anything. Office hours are tomorrow if anyone wants to chat with me about projects or anything else. Thanks for being here. Have fun sweating on your way home.